Welcome students back to the study of electrodynamics. In electrodynamics, first session I dealt with the electrostatics. Electrostatics means study of charges which are static or stationary. In that session, what I had done is I have defined what is an electric field. First I defined electric field from Coulomb's law. And then I tried to find out how I can visualize the electric field by constructing the lines around the charges. And finally, what I was trying to find out is how to quantify the electric field. And the best equation to quantify the electric field under certain conditions, that law is called as the Gauss's law. I have been discussing the Gauss's law in the last session, and I tried to find out the electric field due to a point charge using Gauss's law. Therefore, the Gauss's law was closed integral E dot ds is equal to q by epsilon 0. Now, if I have any type of charge distribution, I have to construct a Gaussian surface. If it is a point charge, I will be constructing a Gaussian surface like this. Therefore, this is an imaginary surface. Imaginary surface. But this Gauss's law has got some limitations. This Gauss's law can be applied only for a field which is symmetric around the charge distribution. Only in such cases we will be able to apply Gauss's law. If the charge distribution is not symmetric, we will not be able to apply Gauss's law. For example, if I have a positive charge, if I want to find out what is the field around it, then I am sure that the field around this positive charge is symmetric. When I say symmetry, what I mean is at a distance 5 centimeter, I have a particular value. At this particular 5 centimeter, I have the same value. At all the 5 centimeter distance, in any direction, three-dimensionally, I will get the same electric field. Then I can say that it is a symmetric field around that charge. If I have a solid sphere, with uniform charge distribution, then also you can see that the field around this solid sphere will be symmetric. Therefore, the Gauss's law can be applied to find the electric field due to a solid sphere. It can be applied to find the electric field due to a point charge. It can be applied to find the field distribution of a linear charge distribution like this, provided you are not interested in finding out the field at the end points. If I am finding out the electric field in between, in the middle of this charge distribution, the field will be symmetric around this line charge distribution. Therefore, if I am concentrating only in this region, then the field will be symmetric, and then I will be able to find out the electric field by using Gauss's law. Therefore, I can apply Gauss's law to find a linear charge, the electric field due to a linear charge distribution limited to a small region, not at the end points. I can find out the electric field due to a spherical charge distribution distributed in the form of a sphere. I can find the electric field due to a point charge distribution. I can find out the electric field due to a plane charge distribution. Provided I am only interested in finding out the electric field. I am not interested in finding out the electric field due to the end points. If I am not interested in finding out the electric field due to the end points, and if I am only concentrating on the region at the middle point, the field will be symmetric around it. the field will be symmetric around it. In that case also I will be able to find out the electric field. Therefore, I can find the electric field due to a point charge. I can find the electric field due to a spherical charge distribution in any form, spherical charge distribution. I can find electric field due to a linear charge distribution, or it can be a small cylindrical form of charge distribution, cylindrical distribution, or I can have a plain sheet of charges. Only in these cases, and the geometry I will be specifically say, I will take each cases and then I will be explaining in detail. In all these cases I will be able to find out, or I can apply Gauss's law and find the electric field. In the case, for example, in the case of a dipole, I have separated two opposite charges separated by a distance. The field lines will be like this. Then you will be able to see that the electric field at this point will not be equal to the electric field at this point. Or for example, if I take an electric field at 5 centimeter here, the electric field at 5 centimeter here, the electric field at 5 centimeter here, they will not be the same. Then I say that the symmetry is not there. That is one way of representing, or one way of saying that the Gauss's law cannot be applied in the case of in the cases of non-symmetric field distribution. Therefore, Gauss's law can be applied only for certain charge distributions. The condition is that the field around the charge distribution must be symmetric. The charge distribution need not be symmetric, but the field around the charge distribution must be symmetric. And the best one was point charge, which I had explained to you, which I had given to you. The first one, the point charge distribution, where I had constructed an imaginary Gaussian surface like this, and then I found that electric field is given by Q divided by 4 pi epsilon 0 r square. Therefore, this is the at every point here at a distance of r, the field will be the same. The field will be the same. Therefore, the equation is Q divided by 4 pi epsilon 0 r square. Now, let us go and find out what is the electric field due to an line charge distribution. Line charge distribution. When I say a line charge distribution, I told you that the line charge distribution can be like this, and charge which is distributed along a line. Therefore, if you have this electric field like this, this will be the electric field on the left side and right side. This will be repelled by the first line, therefore, they will be moving parallel. But what about the end point? The end point will be something like this. And that means here the field is not uniform. Here the field, compared to the other regions, the field is not uniform. Therefore, you have to avoid this end points. I have to avoid this end points. For that, the way is how to circumvent this problem of end point asymmetric field. I will be assuming that the line charge distribution is an infinite line charge distribution. Infinity in physics is a tricky mathematical concept. When I say infinity, actually what I am considering is that a point very near to this line charge distribution. Therefore, at a point very near to this line charge distribution, this end can be considered to be almost at infinity. I am interested only in finding out electric field at a near point of a charge distribution. That is one way of representing, or you can neglect the end point effects. And when you neglect the end points, you are only interested in finding out your charge distribution is like this, your charge distribution is like this. Therefore, I am only interested in finding out the field in a region not at the end points. Therefore, I can construct the field is like this. Therefore, if this is a three-dimensional field, therefore, the Gaussian, the imaginary surface that I constructed will be a Gaussian surface which will be cylindrical in shape. This cylindrical Gaussian surface guarantees that the end points will not be considered. Why? Because the electric field will be having a direction like this. Electric field will be having a direction like this, and then at this surface your area is ds, which is like this, and this angle between the electric field and the surface theta is 90 degree, and your closed integral E dot ds will be equal to closed integral E ds cos 90, which is 0. Cos 90 is 0. Therefore, if you are constructing a cylindrical surface which is only at the, not at the end points, which covers not the end points, then that guarantees that you are only interested in this the electric field at a point very near to it, or we are ignoring the end point effects. Either the two cases you can, either one of the cases you can choose. That is, you can find the electric field at a near point, or you can ignore the end points. Then the field distribution will be uniform around a line charge distribution. Therefore, you have a, that is why people say it is an infinite line charge distribution. Infinity, you are, actually it is not infinite line having an infinite length, or it is not an infinite charge distribution. It only means that you either neglect the end points or you measure the electric field at a near point. Therefore, you have an imaginary Gaussian surface around a large line charge distribution. Therefore, you have a small area here. The area has got a direction like this. Your line charge distribution has an electric field in the same direction. The angle between E and ds, they are given by theta is equal to 0 degree. Therefore, I can apply a Gaussian, the Gauss's law, closed integral E dot ds is equal to q by epsilon 0. Q by epsilon 0. Therefore, this is E ds cos theta. E ds cos theta is equal to q by epsilon 0. This is 1, and electric field, as we are interested in finding out electric field at a particular distance r, everywhere the same distance on this cylinder. Therefore, electric field is a constant. Therefore, I can take that electric field outside the integration. It becomes ds is equal to q by epsilon 0. If r is the radius of the cylinder, if L is the length of this imaginary cylinder, the surface area of the cylinder will be given by the circumference into the length, which will be 2 pi r into L equal to q by epsilon 0. Therefore, the electric field will be given by is equal to q divided by 2 pi epsilon 0 r into L. Now, my charge distribution means the charge distribution is extending to infinity. Theoretically, it is extending to infinity, and the total charges is given by q. Total charges. Now, we do not know what is the charge enclosed by this Gaussian surface, which will be somewhat different. It can be some less than this q. Therefore, it must be q prime, but it must be q prime. But we are not writing that as q prime. What we are doing is, since this is a uniform charge distribution, that is, if you take a small length 5 centimeter, then the charge on the 5 centimeter at every point will be the same, or it is a uniform charge distribution. Therefore, the charge per length, that is linear charge density lambda will be equal to dq by dl. It must be equal to total charge divided by total length also. Therefore, what I am doing is, I am defining this charge enclosed by the sphere as q, and the total charge, I can say that it is capital Q somewhat. The total charge enclosed by this is q, and this q divided by L, I will say that that is equal to lambda. That is the linear charge density. Then by equation for a linear charge distribution, the electric field due to a linear charge distribution, which was given by E is equal to Q divided by 2 pi epsilon 0 R into L, it becomes now lambda divided by 2 pi epsilon 0 R, electric field. This is the magnitude. If I want the vectorial form, the electric field is to be directed in this way. If I have the direction is given by unit vector R, then my equation will become 2 pi epsilon 0 R into unit vector R. This is the electric field due to a line charge distribution. Electric field due to a line charge distribution is given by lambda divided by 2 pi epsilon 0 R into unit vector R. Initially, we found the electric field due to a point charge, which was given by Q divided by 4 pi epsilon 0 R square into unit vector R. This is a point charge. Now you have a linear charge distribution, line charge distribution. The electric field is given by lambda divided by 2 pi epsilon 0 R into unit vector R. We solved two problems. First one was point charge distribution, second one was line charge distribution. Next, we will find out what is the electric field due to a uniformly charged sphere. Third case, we will find out what is electric field due to a uniformly charged sphere, outside the sphere. There are two cases here. One is outside the sphere and the second case is inside the uniform charge distribution. Therefore, when I say a uniform charge distribution, what I told you, now it is a sphere. Sphere means it has got a volume charge distribution. Therefore, it must be a non-conducting sphere. It must be a non-conducting sphere. If it is a conducting sphere, the situation will be different. It must be a non-conducting sphere. If it is a conducting sphere, the charges will be flowing and they will be moving away from each other and they will be spreading on the surface. Therefore, when I put some charges on this sphere, it must be there itself. It must not move. That is why I am taking a non-conducting sphere. First, I will find out what is the field due to the sphere at a point outside the sphere, at a distance r, at a distance r. The total charge distribution, I will once again take that as Q. Q will be, if it is positive charges, it will be NE, where N is the number of charges. It can be 500 charges, 1000 charges, or 10,000 or more than that. It will be uniformly distributed here. Therefore, I can construct an imaginary Gaussian surface like this. The field will be uniform everywhere. I can construct a Gaussian surface at a distance r from the center of this distribution. Simply apply what is the Gauss's law. Therefore, you can construct a surface here. It will be having a direction like this. This is my ds. My electric field also will be in the same direction, similar to the point charge. You will be able to apply this E dot ds is equal to Q by epsilon 0. Same procedure like a point charge, it will be ds because the angle is theta equal to 0 degree equal to Q by epsilon 0 and ds was 4 pi r square. Therefore, you get Q by epsilon 0. Therefore, the electric field due to a spherically distributed uniform charge distribution at a point, the electric field at a point outside will be given by the same equation for a point charge, or you can say that the whole sphere behaves as a point charge as if the whole charge is concentrated at the center of the sphere. It behaves like that, as if it is a single charge. The whole charge behaves as if it is a single charge concentrated at a particular point which is at the center of the sphere and will be given by Q divided by 4 pi epsilon 0 r square, and if it is a vector into unit vector r. Therefore, we found the equation for The electric field due to a point charge, electric field due to a line charge distribution. We say it is an infinite line charge distribution. And the third one, we found out the electric field due to a uniformly charged sphere outside the sphere. Now, my aim is to find out what will be the electric field inside the sphere. What will be the electric field inside the sphere? Same sphere with the uniform charge. The charges cannot move. That has to be guaranteed. Only then you can say that it is a uniform charge distribution. Now, I consider a center. This is the center. I consider a sphere Gaussian surface like this. This is distance r. Therefore, if the total charge distribution is q, the charges, if this is 1000 charge, this will be contained in the whole sphere. I cannot say that the whole charge is inside this sphere, and let the charges be represented by q prime. Let the charges be represented by q prime. Now, my aim is to find out what is the electric field at this point. Therefore, let me apply the Gauss's law. Closed integral E dot ds is equal to not q by epsilon 0, it is q prime by epsilon 0. Q prime I do not know. Because when I say I do not know, somebody can construct a Gaussian surface at 5 centimeter, somebody can construct a Gaussian surface at 10 centimeter. That is his choice. Whoever is drawing it, he can choose 5 centimeter, 10 centimeter sphere. Therefore, I cannot guarantee, I cannot say that q prime is known to me. Therefore, q prime is unknown to me. That has to be taken into consideration. Later, I have to write what is known to me is q. Initially, I have deposited some charges inside the sphere. Therefore, that is known to me. I had considered a sphere with so much charge distribution. Therefore, q is known to me. I have to finally write my q, the electric field in terms of q only. Therefore, the same way of representing, you can consider an area like this. Therefore, the same equation comes just like a point charge, just like a sphere outside point is given by q prime by epsilon 0. Therefore, electric field is q prime divided by 4 pi epsilon 0 r square. This is an unfinished result. You cannot say that this is this result is the right one, because you do not know what is q prime. Q prime is unknown to me. Therefore, I have to write that q prime in terms of some known parameters. For that, I know that it is a uniform charge distribution. Therefore, the charge density is a constant. Therefore, if I take the radius of the sphere as capital R, the charge density is given by total charge divided by total volume, 4 by 3 pi r cube. And now, the same thing will be, since it is a uniform charge distribution, that will be q prime divided by 4 by 3 pi. The radius is small r. Therefore, this 4 by 3 pi and 4 by 3 pi cancels. Q prime is equal to small q into r cube divided by capital R cube. Okay. R is chosen by me, capital R is already known to me, q is also known to me. Therefore, I can rewrite this expression as q prime must be replaced by q r cube divided by r cube, and my old parameters are 1 by 4 pi epsilon 0 r square. Therefore, this r square and this r cube goes and one r remains there. It becomes q r divided by 4 pi epsilon 0 r cube. Therefore, the electric field inside a sphere at a point r is given by 4 pi epsilon 0 r cube. I can rewrite this expression once again. I will multiply by 3 and divide by 3. Therefore, this is 4 by 3 pi into r cube, and this is q, which is nothing but the charge density. Therefore, this is rho r, remaining things are 3 and epsilon 0. 3 epsilon 0. Therefore, the electric field due to a uniformly charged sphere, you will be able to get that as E is equal to rho r divided by 3 epsilon 0. And if you want to represent that vectorially, I can write that rho r divided by 3 epsilon 0 into unit vector r. Therefore, what we have studied is, we have studied about a point charge which is given with point charge. I had point charge, field due to a point charge, field due to a line charge, field due to a spherical charge distribution, inside and outside. Field due to a spherical charge distribution, inside and outside. Now, the next case is, what I have taken is a spherical charge distribution which is a non-conducting one, Now, what will happen if it is a metallic conductor, metallic substance, if that sphere is a solid metal, and I try to deposit charges on it. When I try to deposit charges on it, for example, if I start depositing 2 positive charges, they are dead against each other, and what they do is they will repelling each other and they will be moving to the end points. If I deposit 2 or more charges, they will be moving to the diametrically opposite points. And then any charge, if I deposit inside a metal which is a solid one, all the charges will be moving to the surface. Or in the case of a metallic surface, whether it is, if it is a solid one, you will never be able to see any charge inside this metallic solid substance. All the charges will be residing on the surface of the metal. Therefore, if you construct an imaginary Gaussian surface, there is no charge inside. Therefore, the electric field inside a metallic solid will be always 0. Electric field inside a metallic solid, and the outside, it is as usual. In the case of a charge distribution, you studied for the case of a sphere, outside is given by q divided by 4 pi epsilon 0 r square. Therefore, electric field outside a metallic sphere will be given by E is equal to q by 4 pi epsilon 0 r square. In the case of a hollow sphere, the same thing is there. If it is a hollow one, you will not be able to deposit charges inside the sphere. Same result. You will be able to get the electric field only outside. Electric field inside a solid or a hollow metallic sphere, it will be always 0. Therefore, now we have studied about point charge, line charge, spherical charge. 3 cases we have studied. One is a uniform charge distribution which must be a non-conducting or a non-metallic one. Then we studied about a metallic sphere, and we studied about a metallic hollow sphere. You will never be able to get electric field inside a metallic or a conducting object. If you extend this to any conducting object, the field inside a cavity, a metallic cavity or a conducting cavity, field inside a conducting cavity of any shape, you will never be able to get to the field inside a conducting one. For example, in the case of lightning, if you are sitting inside a room, the room that we had constructed is on the surface of the earth, and the earth is the best conductor that is available. Earth is a very good conductor of electricity. Therefore, the walls also will be conducting one. Therefore, whenever a lightning comes and strikes this building, the electric field will not, since it is a conducting one, the electric field cannot penetrate inside this one. Therefore, people ask you to sit on a table or any wooden substance, either a cot or a table. Whenever there is a lightning, you are asked to sit on a wooden non-conducting substance so that you are not getting this lightning. Since if you are standing on the surface or on this the basement of this house, there is a chance that the lightning is a good conductor. If this is a good conductor, lightning may go like this and you will get electric shock. But if you are standing or sitting on a non-conducting wooden table or something like that, then the chance of getting lightning will be very less. Why? The reason is the electric field inside a conductor will be always equal to 0. Therefore, the electric field inside a metallic conductor or any conducting substance, that will be equal to 0. That is the benefit of studying this electrostatics applications. You will be able to see that the electric field inside a conductor is equal to 0. Now, in one more case, I will be studying electric field due to an infinite plane sheet of charge. Infinite plane sheet, charges are distributed in the form of a sheet. Charges are distributed in the form of a sheet. The same idea I will be considering. I am not interested in finding out what are the effects of the edges. What are the effects of the edges? Therefore, I have a charge distribution like this. If I have a charge distribution like this, I am not bothered about the end points. I am only bothered about the charge distribution well inside this plane sheet. The lines will be like this. The lines will be like this. I can construct a Gaussian surface like this. But the point is that the Gaussian surface will be, or the lines will be spreading on two sides. Therefore, the Gaussian surface that I construct must have an area on both sides. And this Gaussian surface, this area, there is an elemental area. If I consider here, the field lines will be like this. The area is like this. This angle is theta is equal to 90 degree. Therefore, don't bother about the curved surface. I am only interested in finding out the lines passing through this area. I will be interested in electric field passing through this area. And this will be having, this electric field lines will be in this direction. The surface will be having this direction. Therefore, theta will be equal to 0 degree. Therefore, closed integral E dot ds is equal to q by epsilon 0. Therefore, this E I can take outside. Area ds is equal to q by epsilon 0. But the area that you have to consider is two areas are there. One area is on the right hand side, one area is on the left hand side. Therefore, this small elemental area, if you integrate, I have two areas will be there, q divided by epsilon 0. As in the case of line charge distribution, there is an uncertainty in the charges enclosed by the Gaussian surface. Therefore, I will not be able to find out what is q there. Therefore, to escape from that, I will take that q by A as the surface charge density sigma. Then my equation will be sigma divided by 2 epsilon 0, where sigma is equal to q divided by A. And if I want it in the vector form, I can take some unit vector n, which is a vector perpendicular to this plane surface. Therefore, my electric field will be given by sigma divided by 2 epsilon 0. Electric field which is perpendicular to the plane surface, infinite plane surface, will be given by sigma divided by 2 epsilon 0. In my first session, I tried to define the electric field, and then I modeled the electric field, and this second session I tried to find the applications of Gauss's law with which I will be able to find out the electric field. We worked out the examples of point charge distribution, line charge distribution, spherical charge distribution, and finally we solved the equation for the electric field due to a plane charge distribution which is having an infinite area. It is having an infinite area. Infinite area guarantees that that field on the either side of the plane sheet will be uniform. And the next session I will be doing some problems based upon the things that we have studied in these two sessions. We had applied the Gauss's law to find the electric field due to some charge distributions. We studied about the line charge distribution, then we studied about the spherical charge distribution for conducting and non-conducting cases, and then we found out what is electric field due to a plane sheet of charges. which is an infinite plane sheet. The infinite plane sheet guarantees that we are not interested in finding out the field at the edge points of the surface. Actually, you will be able to see that these are the examples that are given in any textbook. No other examples we will be able to apply Gauss's law. Only for these cases, in any textbook all around the world, if you search, the only examples that you can see is these ones, because these are the only examples where you will be able to have a spherical field about any type of point charge distribution. In the next session, I will be dealing with, or I will be working out, since our aim is to do some problems connected with the UGC examination. In the next session, I will be working out some problems, simple problems connected with this electric field. Until then, goodbye.